Good morning, everyone. Welcome to our unusual Thursday slot of the seminar series. It's a great pleasure to introduce to you our speaker of today, Andres Garcia Saavedra. Andres was a PhD student here at UC3M, and it seemed to me it was just recently when I attended his defense, but it was 8 years ago. And then Andres went to Trinity College Dublin in Ireland as the research fellow, and since 2015, he was with NEC Europe, but physically here in Madrid, doing some exciting work. And today is work that are going to be presented at Mobicom. So Mobicom had no conferences this year. Next year, we'll have two conferences, including the first one in late January, beginning of February, which will be called Mobicom 2021. So in my email announcement, I said it's going to be dry run, but actually Andres will give a kind of larger talk to present the work in more detail. So before allowing Andres to continue, I will ask my usual question whether Andres is fine with recording, storing, and publishing the video of the presentation.
Yes, no problem.
Okay, Andres, please go ahead.
Okay, so thank you for coming and for joining those of you that are remotely. So like Sergey said, so this is a piece of work that we presented in Mobicon this year, although the presentation is in February. But I wanted to remark that this is not a dry run. So that means that you don't have to hold your questions to the end if you have questions. Actually, I would prefer if you had questions at the moment as I'm explaining something, you bring those up just for the sake of discussion, okay? So don't hold back on your questions. So yeah, so the title is Nuberu, Reliable RAM Virtualization. And yeah, this is about making base stations or virtualized base stations reliable. I will explain how this is particularly challenging, more challenging for base stations than for any other network function in a mobile network. And I will explain how, the state of the art is struggling to actually find proper solutions. And well, I will present our own approach to this problem. Of course, credit to who is due. Here, you can see at the bottom some colleagues from here in the UC3M, and a special credit to Gines, who's actually the guy that did most of the heavy lifting in this work. Okay. So a little bit about the motivation of the problem. So I just said a few words about it, right? So I just introduced that virtualizing a base station is hard, right? Harder than any other network function in a mobile network. And the main reason is because, when you look at the architecture for a base station, you will see that it's typically decoupled into, for 5G particularly, into three sort of functions, right? One is the radio unit. You can see it in orange in the top left corner. The radio unit is basically the antenna, and it does very basic signal processing functions, like, for example, amplification or signal sampling. Well, it's basically the antenna, and it's a piece of hardware that is harder. It's not for discussion for virtualization in this talk, right? Another function is the distributed unit, or DU, that you can see on the screen, and CU, or central unit. Basically, the distributed unit contains all the lower part of the protocol stack of the base station, including the physical layer, the MAC layer, and the radio link control layer, right? Whereas the central unit basically processes the highest layers of the protocol stack of a base station, which is basically the PDCP layer, for those of you that are aware of the architecture of a base station. Now, so virtualizing a CU is easy. Basically, a CU, if you simplify this a lot, you can think of a CU as a normal a special switch, let's say, that forwards packets. Basically, virtualizing this type of network functions has been successfully done for many years now. So it's not particularly challenging today, right? Now, the challenge is to virtualize the distributed unit, right? Why? Because it holds the physical layer OSMAC layer, but especially the physical layer. And the physical layer has to process or has to perform a number of functions that have very tight timing constraints. Not only they are tight, so you have to process these tasks very, very quick. It's important that the processing time in these tasks are deterministic, right? Meaning if you have jitter, or if there are fluctuations in the processing of this task, you will get into problems. And I will show you later what these problems are, right? So basically, the way virtualize or the way manufacturers today, like NEC and all the others really, provide solutions for virtualized base stations is basically to offload these time-critical operations to a hardware accelerator. Okay, this is a sort of an obvious solution that, of course, the market is currently implementing. Right now, I will argue here that this is not a proper solution for virtualized base stations, and maybe we can discuss about it later, right? And because and the main problem is that this is a very expensive solution, right? Basically, for every distributed unit, for every base station in your network, you have to include a hardware accelerator, which is an expensive piece of equipment if you compare to the remaining of the base station, and it consumes a lot of energy, right? And as I will show you later, so having a virtualized base station with the assistance of a hardware accelerator may give you a reasonably performing base station, but the cost of this base station is much higher than a traditional base station that is not virtualized. And now this is a huge problem, because the whole point of bringing virtualization to the radio access network is to reduce costs and increase flexibility. And it turns out that the current methods that we have to actually implement this give you the completely opposite result, right? So what I will argue is that still we shouldn't sort of give up in this. I think it's still important that we look into this problem and we eventually manage to implement virtualization in the base stations, because I still think that virtualization will bring lower costs and higher flexibility than the traditional way of implementing base stations. Now, in my opinion, the path to achieve this goal is not through using dedicated hardware accelerators, but to share hardware accelerators. Okay, so if we share hardware accelerators and we provide, abstraction layers between the accelerators and the base stations to properly decouple software from hardware, we can still take advantage of the processing speed of these hardware accelerators to do some of these time-critical operations, but we alleviate the cost because we are distributing the cost across multiple players, right? This is sort of obvious. Of course, this is not obvious, right? Because, yeah, we still have very fast processing of some of these tasks, but we haven't get rid of fluctuations now. Now, because we are sharing, we have sort of a queue somewhere in the system where base stations will actually issue the request to perform some time-critical operation, but there will be competition for access to the hardware accelerator, right? And because there is competition, there's a queue, there will be fluctuations in the amount of time it takes for one operation between request and service. And this is a problem. Okay. So we need, and the whole goal of this approach is in this context where we have non-deterministic computing performance, like in shared computing platforms like this one. The whole goal here, or the whole objective of this work, is basically to attain reliability. So here I have a couple of statements from two top executives in the business, one from Ericsson and one from Nokia, which essentially made the same point I just made here. That virtualized base stations are very interesting as a research study, but currently commercially is certainly not a viable solution because they render more expensive and more energy consuming base stations than their traditional counterpart. So from a business perspective, there's really no advantage at this moment, right? So we need to look into different approaches to do this. So this slide presents a little bit on the state of the art on some people that have looked into this problem. So the first two bullets actually present some solutions for hardware acceleration of some of these physical layer operation, mostly forward error correction coding. LDPC decoding is typically the task that is more challenging to actually process in time, and therefore most of the research focus on this operation, right? So the first two, the first coming from Intel FlexRun, and the second two coming from NVIDIA, called NVIDIA Aerial, are two solutions, two sort of drivers that can actually offload these forward error correction operations into a hardware accelerator. In the case of Intel, they offload this operation to an FPGA. And in the case of NVIDIA, obviously, it's a solution to offload this time-critical operation to GPU. And I don't have results here to show you, but I mean, you can. It is rather intuitive that these hardware accelerators can provide orders of magnitude improvement in terms of latency when processing these tasks than a normal CPU. Right. However, as I said, of course, we need these sort of devices to offload these tasks, but the problem is how to actually share hardware accelerators across multiple base stations or distributed units. In the third bullet here, I have presented a solution from people from Microsoft and Yale. This is a solution called Agora and was presented in Connex 2020. And here their approach is essentially to get rid completely of hardware accelerators. Basically, it's a rather impressive piece of work where they try to implement a high-performing base station that is capable of doing massive MIMO with up to 64 antennas without any hardware accelerator whatsoever, which is actually challenging to do, right? They did achieve this. The only problem with this approach is there is no way you can have multiple base stations sharing the same computing infrastructure. And the problem is that, yeah, they managed to do all these, the operations of this base station with CPUs, but you need many CPUs. And eventually you end up having the same problem, a very expensive computing infrastructure with a huge amount of energy consumption, right? So yeah, it's interesting as a research activity, but really not commercially viable, really. Another very interesting piece of work was presented this year in SIGCOMM, also for people from Microsoft, a different group though. Basically here, what they try to do is, okay, we have a base station, and a base station has, you know, very distinct workloads, where most of the time the computing infrastructure is not used. Yeah, this is common for many networking functions. And here, what they try to do is essentially, okay, those computing cycles, those CPU cycles that are not used by the base station, let's see if we can use them for other applications. Like, and essentially what they did is they created a sort of a task scheduler where they prioritize the task of the base station, and therefore the remaining CPU cycles that are not used, they let another third-party application to use those, right? Now, the problem still remains. Yeah, sure, when you have a high-priority application, like a base station in this case, another non-priority applications that can take advantage of the remaining cycles, so it's not easy, but it still is not the solution to virtualize runs. Here, what we want is to have in the same system multiple base stations with equal priority sharing the same computing infrastructure, right? And to show you a little bit of the impact or the problem, or how or why virtualizing base stations is more difficult or have more serious consequences than in a normal networking function, we did an experiment. Here, this is shown at the bottom. This is a very simple experiment, right? So here we took a on-off-the-shelf server with 5 CPU cores, not particularly high-performing CPU cores, and here we deployed 2 virtualized distributed units. These virtualized distributed units are based on SRS-run, which maybe some of you have heard of. This is an open-source LTE stack, right? So we took 2 instances of these distributed units, and we placed them in the same settings, in the same computing platform. Here we are not doing any special CPU scheduling across these distributed units. We are using a default Linux scheduler to allocate CPU resources across these 2 VDUs, and both of them have the same priority and nothing special there. So what we did here is with the purple line, we are presenting the throughput of one of these base stations, okay, base station 1 or distributed unit 1. Okay, this distributed 1 is trying to transmit and receive from an UE as much traffic as possible, right? And we measure how much is successfully transmitted and received with respect to the capacity of the system. So it's a relative metric here that goes from 0 to 1, right? Now, in base station 2, what we did is we started off with very low load, right? If we are in the left-hand side of the x-axis of this plot, base station 2 has very low load, right? So which means that it's stealing CPU cycles from base station 1, very few cycles, CPU cycles from base station 1. So the competition for access to the computing infrastructure is very small at this moment, because VDU 2 is not really demanding a lot of them, right? And therefore, when the computing interference of this second base station is low, the throughput that we get with this with base station 1 is high, the maximum possible, right? But as you can see, as we gradually increase the load of this base station 2, we are also increasing the computational demand of this second base station, and therefore we're increasing the competition for computing resources. As you will see, at some point, the computing interference of this second base station is so high that it completely breaks base station 1, right? So this is not a gradual decrease in performance, which is something that you could see in normal network functions, virtualized network functions, like a virtual switch. In a virtual switch, you could see, okay, you may miss some packets being forwarded, some processed. So you could see some gradual degradation in normal virtual network functions. This is not the case for virtualized DUs. Virtualized DUs, when you have sufficiently high computing interference, you are completely breaking the system. I will explain the reason why, but this is basically because now the base station is not capable to delivering signals in time to the users. And because the users cannot detect those signals, they lose synchronization with the base station. And therefore, there's no communication anymore. So throughput goes from 100% to 0%, right? So that's why it's critical to make sure that we achieve reliability in these systems, to make sure that throughput is high at all times, to make sure that the signals that the users have to receive for synchronization and other important control operations are always received in a timely manner, despite the computing fluctuations that you may have in the cell platform, right? So, okay, I'm anticipating here a little bit, but as you would have expected, we have a solution to this problem, right? This is, sorry, I changed the colors on this plot. Now the baseline is the yellow, and our solution, which we have called Nuberu, is the purple. And as you can see, repeating the same experiment here, we managed to actually have 100% throughput for the base station 1 in this case. And I will explain later how we managed to do this. Again, feel free to stop me at any time and make questions. Okay, so here I'm summarizing a little bit the main idea behind our solution. I will detail this idea later on, but this is essentially the essence of it, right? So here the main idea, and the idea is rather obvious, right? Here we have a base station that has to process many signals. Some of these signals are carrying uplink data from the users to the base station. Some of these signals are carrying downlink data from the base station to the users. Some of the signals are carrying control data, both in uplink and in downlink. Some other signals are there just for synchronization between the users and the base station, or even just for measurements to actually being able to estimate the channel, the wireless channel. Right? So there are many channels and many signals there. So the solution, and of course we want to protect the ones that are devoted for control and synchronization, because they are obviously more important than those for data. So if you end up in a situation where you have deficit of computing capacity, then you have to make a choice. Do you protect critical control information, or do you protect data delivery? Obviously, in these situations, you could protect control information at the expense of data delivery, because okay, if you have to sacrifice some throughput, that's fine, as long as you preserve connectivity. So some throughput is better than nothing, right? So, and this is what we did. Very simple idea. And we came up essentially with the concept of minimum viable subframe, which is basically a subframe, a set of signals that are required by the user to preserve connectivity in the worst possible case, right? And then our whole goal is to make sure that despite what's going on in the shared computing infrastructure, we manage to build this minimum viable subframe. So we preserve synchronization and connectivity with these users at all times. Now, once we manage to build this minimum viable subframe, then, okay, we do best effort data processing stuff. So we try to communicate to process as much uplink traffic from the users and as much downlink traffic to the users as possible, right? So we protect critical operations, and once we make sure that those are protected, then we do whatever we can to deliver as much traffic as we can, right? Now, the idea is very simple, it's obvious, really, but it's not really easy to implement. The main reason is because all these tasks, data processing task, the uplink downlink, control processing task, downlink uplink, synchronization signals, all of them are coupled between each other. So we cannot really take all these tasks separated and then make sure that the important ones are done and then we do the rest. That doesn't happen this way because they are coupled. So for instance, in order to compute the scheduling grants that go into the downlink control channels in the downlink subframe, we first need to decode all the data from the uplink because we need information from this process in order to make scheduling decisions. Or in order to make in order to process data in the downlink direction, we obviously need to make scheduling decisions before. And also we need to decode all the uplink signals because in the downlink signals, we're carrying feedback for the users about if their uplink data were decoded or not. So there are couplings there. So we cannot decode data without having decoded, downlink data without having decoded uplink data before. So there is a pipeline of tasks that have to be processed in a sequence. And this is a problem because it doesn't let us separate them in order to prioritize. So in order to actually do this, we essentially came up with three sort of hacks, really, to the regular pipeline of operations of a distributed unit. The first one is sort of a two-stage downlink scheduling approach. This is basically the regular scheduling approach of a normal base station, but we split it into different subtasks, let's say. And this, as I will explain later, this actually let us sort of trade off reliability for delay. So we can actually, by separating the scheduling into two subtasks, we can actually hold back processing downlink tasks till we make sure that the control tasks are processed. The second trick that we implemented is what is called early HARQ. So HARQ is an important process in cellular communications because this basically gives you protection against error in the wireless channel, right? Basically, the way this works is we have to encode through different codes the signals, and the receiver you have to decode them. In 5G, you use LDPC decoders. In 4G, you use turbo decoders, right? And it's called hybrid ARQ because you also use ARQ. So you need feedback from the users to the base station and the other way around, right? So here what we did is this early HARQ, which is essentially make a prediction on the decodability of data, right? Because at some point we need to send feedback to the users. But in order to send feedback to the users, we need to wait for the data to finish the decoding process. Now, this takes a lot of time. So what we do is we don't wait for the decoder to finish. We make a prediction somewhere in the way, and then we tell the users whatever prediction we make instead of the real thing, right? This let us decouple the decoding process of uplink frames from the actual provisioning of feedback to the users. And the last approach is a very simple idea as well, which is congestion control, basically, right? So essentially, the computing demand of a base station largely depends on the amount of data that you schedule to the users, right? So here, what we implement is a very simple feedback loop where we adapt the size of the data scheduled for the users, which is called transport blocks in 3GPP. So we essentially adapt the size of the data that we send and receive to the from the users. We try to adapt it to the computing capacity of the system, right? And we implemented a very simple feedback loop to achieve this. So a little bit more details about the sort of the head of line blocking problem that we have in this pipeline, right? So essentially, when we have a distributed unit, we have to perform a pipeline of operations. The first operation is always FFT, right? This is usually, if you go to Orange specification, this is done at the radio unit. Okay, so what you receive are symbols basically at the distributed unit, and the first thing that you do is you try to get from all the symbols that you have received, you go to those that are about uplink data channels, right? Those are we go to the symbols that are about uplink data from the users, okay, which are actually shared in the same uplink data channel, right? And what we do is we process all those symbols, meaning that we demodulate all the radio blocks, we decode the transport blocks of those users, we do red matching, we do all the pipeline of operations that have to do to process these signals basically from the uplink channel. The next thing we do is we process the control channel of the uplink, right? So we go to the symbols that are about uplink control information, essentially stating things like, for example, the users telling the base station that they want to transmit something. Okay, there is a signal there in this channel, so for the user to actually let the base station know that they have data to be transmitted, please schedule me some radio resources to transmit this data. So that's also to communicate the base station feedback of the channel, for instance. So this is what this control channel is used for. But of course, and the next step is actually compute grants, basically making scheduling decisions. But of course, we cannot compute grants before we have processed the uplink control channel and before we have processed the data channels. Why? Because in order to schedule radio resources for the users, we need to know if we need from the uplink data that they have transmitted, we have to know whether we have to schedule retransmissions or new transmissions, for instance. We also need to know where the users want resources to be transmitted, that information that goes into the control channel, or we need to know the wireless channel of the users. So we decide on the appropriate modulation encoding scheme for these users. So therefore, we cannot schedule data before we process the uplink control channels, right? So that's why this has to be done after this operation. The next operation is essentially processing downlink data channels. Once I have done scheduling decisions, I take advantage of this time and I send data for the users and process downlink control channels, basically with information like, for instance, scheduling decisions for the users. Now, what matters here is that there is a latency constraint to perform this set of operations, right? And usually this time constraint in LTE is fixed, is 3 milliseconds. Okay, you need to perform this operation in 3 milliseconds. Otherwise, the user will not be able to receive this downlink subframe. And in 5G, this is configurable, but the usual number is also 3 milliseconds. Okay. So that's why typically, so like I said, processing all these channels is another pipeline of operations. One of which is the forward error correction coding, which is typically offloaded to a hardware accelerator. And this is essentially what we want to avoid, to offload this to a dedicated hardware accelerator. So we have these 3 milliseconds of latency to perform this operation, right? Now, there is no gain in processing this pipeline of operations before 3 milliseconds. So here it's not about minimizing latency, right? Of course, there's a huge consequence if you violate this deadline, right? But you don't want to minimize latency. You want to actually get it right. You just need to make sure that the pipeline of operations is done in 3 milliseconds, not necessarily earlier than that or faster than that, right? And essentially, what in the experiment that I presented to you earlier, this is essentially what's happening, because at some point the computing capacity of the system is lower because there is computing interference for another base station. You know, all this set of tasks cannot be completed in this time constraint. And because it cannot be finished in this time constraint, this subframe these signals that go into the downlink direction will not be able to be detected by the user, because they're transmitted at a time where the user does not expect it. Okay, and therefore the user loses connectivity with the base station because it loses synchronization with the base station. Now, what we did is essentially try to decouple first to figure out which are the operations that actually take longer time. This was easy. This is basically data processing channels and both in the downlink and the uplink direction, because on the coding and the decoding operations, right? These are these operations in red in the picture, right? And what we try to do is to decouple them from the rest of the pipeline. And that's what you can see at the bottom, right? So here you can see at the bottom the green boxes. This is essentially the data processing tasks, both uplink, the one at the top, and the other one downlink at the bottom. And the rest of the tasks remain there in the same pipeline. And what we do is we establish a hard deadline, which is here depicted in blue. Okay, we establish a hard deadline in time that we make sure that the remaining tasks to build a downlink subframe can be done in time, right? Irrespective if the data processing tasks have completed or not, right? So here's the point: if the data processing tasks do not finish before the blue deadline, we do something with that information, but certainly that information is not going to go into the current downlink subframe. So after this deadline, we compile a downlink subframe with whatever information we can to make sure that the base station, so the users can still receive a downlink subframe to preserve synchronization and connectivity, right? Now, doing this again is sort of obvious, but it's not so easy because of the dependencies between tasks that I just mentioned. Okay, this is of course a simplification of the tasks that have to happen in the distributed unit. In reality, it looks more like this. I'm not gonna explain this, of course, but I just wanted to present this picture because the blue arrows show dependencies between the tasks. And as you can see, this is a complicated picture with a lot of blue arrows, meaning there's a lot of dependencies between tasks. So decouple these tasks is certainly not easy. It's an important engineering effort. Right. So the first approach that we did that I anticipated earlier is this two-stage downlink scheduling approach, right? So here the idea is that, okay, at the very beginning of the pipeline, what we do, which is not usually done, is we compute downlink grants with whatever information we have at that point in time, right? And with those grants, which is essentially data to send to the users, we start processing those grants in a separate thread, right? And this thread is encoding or processing this downlink data in parallel, right? And once they are done, it can happen two things. In the bottom part, there's a green downlink transport block that is finished being processed before the blue deadline that I mentioned before. If this happens, great. We have encoded downlink data before the deadline. That means that we can actually place this data into the downlink subframe that I have to send to the users, right? If not, which is the orange case, if the encoder exceeds the time deadline that we have set, right? What we do is we just store, once it finishes the encoding this data, we just store it in a buffer, as simple as that, for actually to try to take advantage of this encoded data for a later subframe. Very simple. Now, in the second stage of the scheduler, essentially we look at this buffer and we take those that are ready at that point in time, and we of course discard those that are not ready, potentially to include them in a future download subframe. So also pretty intuitive, I think. So the second approach that I also anticipated earlier is this concept of early HARQ, right? Now, another problem that we have is in order to compute grants, we need to wait for the decoder to finish decoding all the transport blocks that the users have sent to us, right? Of course, here, what I'm trying to tell you or convince you of is that we cannot afford waiting for the decoder to process all these things, right? So what we do is we make a prediction with the best information that we have at the moment, right? So when the blue deadline hits in, basically, either you have finished the coding, which is the green rectangle at the top. If you have finished the coding, fine. We actually use the result of this process to send feedback to the users accordingly, right? But if you didn't have time to process the uplink grants in time, which is the orange case by the blue deadline, what we do is, okay, we make a prediction, and then we rely on the prediction for feedback, right? I'm not going to explain how we do this prediction because I will have to explain how a turbo decoder of an LDPDC decoder works, but essentially we use extrinsic information. So these are iterative processes, right? And for every iteration, so they iterate over the data that you have received, and for every iteration you try to improve how confident you are that your bit is a 1 or a 0, basically. And there are some numbers there that gives you some indication on how confident you are as you go iteration over iteration, basically. This information is called extrinsic information, and it's encoded as log likelihood ratios, basically. So essentially, I'm not going to explain how we do this, but we take this information and the pattern, the evolution over time of this extrinsic information, and we make a prediction. For instance, if we start from very low, near to 0 log likelihood ratios, so confidence on what the data actually is, but when the blue deadline hits in, I have very high confidence, that means that I can say with high confidence that at some point I will be able to decode this data because the trend is positive, right? However, if from the first iteration to whatever iteration I ended up when the blue deadline hit in, this information about how confident you are on what each bit is has not changed. That means that this is likely that even if I let you continue on, you will not actually be able to decode this data. So I'm not going to explain the details, but this is the intuition behind it. Essentially, we look at this, the way the decoder has managed to extract information out of the symbols that it has received, and then we make a prediction, as simple as that. And then we use this prediction to actually make scheduling decisions and build a Downlink subframe accordingly. Good thing is that once we, yes.
You have to use these predictions. I mean, the prediction is not 100% perfect. So you are missing the results, but how is this then affecting? How inaccuracy the prediction affects?
Yeah, that's a very good question. So I'm going to repeat the question for the people that's remote. So essentially it has to do with what is the consequence of making mistakes when you make a prediction. Because we're making a prediction, it is certain that we're going to make mistakes at some point. Right? Of course, we built a mechanism that is, has high rate of positive predictions and so on and so forth. But in any case, as with any prediction mechanism, you will at some point make a mistake, right? So what happens with the situation? So what happens is there are two possibilities, right? Either the transport block that you are trying to decode cannot be decoded because the signal is very bad, right? And so that means that you have to tell the users to retransmit, but you predict otherwise. You think that you are able to decode. So you tell the users do not retransmit, right? So what happened here, this is the worst possible case, because in that case, there is nothing we can do. In the sense, we just rely on higher layer recovery mechanisms. So in cellular networks, there are two parts where we do error control. One is this one at the physical layer. The other one is at the RLC layer, although this one is optional. So at the RLC layer, there is another ARQ mechanism. So we trust on RLC's ARQ mechanism to record this data. Or if you have that option deactivated, which is possible, then we hope on TCP or bad luck. The other case is simpler, because the other case is if you make a mistake, in the sense that you predict that you are not going to be able to decode it, but the worker or the process eventually managed to decode, this is okay, because yeah, you will ask the user to retransmit data, but it's not too bad. Yeah, it's not too bad. So moving on, the last approach is also very simple. As you can see, all these approaches are sort of individual, very simple ideas put together into a whole system. So this, and in essence, is also a bit also about prediction, right? So here, what we try to do is, like I said, so the computational demand of the base station highly depends, or largely depends, on the size of the data that you send to the users or schedule to the users, because the time it takes for the decoder to decode data sent from the user is proportional to the size of the data that they send to you, right? And the other way is the same. So if the time it takes for an encoder to encode data for the users is proportional to the size of the data you send to the user, right? So intuitively, if we manage to control the size of this data, we can also control the demand for computing resources, right? So what we implemented here is a very, very simple congestion controller based on the feedback that we get from the other two schemes that we presented earlier. In the case of the downlink, basically every time we miss this blue deadline, when we are processing downlink channels, we tell the congestion controller to reduce a congestion window. Every time I successfully encode data with in time, I tell the congestion controller to increase the congestion. So a very simple additive increase, multiplicative decrease algorithm, which is common in TCP and many other approaches. So super simple. In the case of the uplink, a little bit of the same, right? So every time I make a correct prediction, then I tell the congestion controller to increase the congestion window for the uplink. Every time I make an incorrect prediction, I tell the congestion controller to reduce the congestion window. Now, here there's a difference here, that for the uplink, I'm not considering the deadline to actually inform the congestion controller to reduce or not, because I don't care if the decoder took longer time than the deadline to decode that, as long as the amount of information that is provided by the decoder by the blue deadline is enough to make a good prediction. That's what I care about. So I don't care whether it finishes or not. By that time, I care that the information that actually it provides us with is sufficiently good to make a good prediction. And so very simple. So I'm not going to get into that. It's very simple feedback loop to try to control the size of this data to the fluctuations of the computing capacity. Now, of course, this is a very simple algorithm, and I want to make a point here, which is about the simplicity of all these schemes. Now, if you want to deliver a real system, it's very important that all these methodologies or methods are extremely simple. Why? Because the time it takes for them to run affect the overall time of the pipeline. So if I'm trying to here do some, if I have a time constraint of 3 milliseconds, by my prediction for the early HARQ stuff takes 3 milliseconds, then I'm doomed, right? So I need to rely on very simple prediction mechanisms, on very simple congestion control algorithms, right? So this is very important, and basically this applies in most of the networking problems. Yeah, let me go first to it.
So what happens if you end up before the pipeline?
Nothing. It's as good as finishing it in 3 milliseconds. There's no benefit out of finishing all this pipeline before 3 milliseconds, before the red deadline in this picture. Sorry, for those on remote. So I was asked what happens if the whole pipeline of tasks finishes before the red deadline is here. And I'm not sure I understood.
So the thing is, you end up all the consecutive tasks that come after are affected, or you don't have always the 3 milliseconds time. You have 1 millisecond.
No. So you have 3 milliseconds to finish all these tasks. Doesn't matter how much time each individual task takes. Finishing tasks very soon doesn't help. The whole point is that the whole pipeline of tasks finishes before the red line. But there is no advantage of finishing earlier the whole pipeline. There's no advantage on individual tasks. Of course, the faster processing these tasks are, the higher the chances you have that the whole pipeline finishes in time. That's why commercial solutions use of hardware accelerators. That's a way of doing over-dimensioning. So you make sure that the important tasks are super fast. So you are sure that in the worst case, all the pipeline will finish in time, right? But this is a way of over-dimensioning, right? Really, if we are picky, what the point of operation where you want to be at is where the pipeline of tasks finishes exactly at the red, because that means that the amount of computing resources that you have in your system are optimal. So you're not over provisioning or under provisioning in that case. Of course, this is not easy to do because the computation in the model system fluctuates with the demand of the users, with the channel quality of the user, with many things. So you cannot change the computing infrastructure as fast. But yeah. Yeah, Marco.
Yes, now it's about my question. So when you congestion control, what is it actually, or how is it actually implemented? So what are you controlling it?
Yes. So in sort of the first hack or trick that we make here is separating the scheduler into two subtasks, right?
Andreas, sorry for interrupting, but I think we didn't get the Marcus question. So can you repeat?
Sorry. Yes, good point, Sergey. So Marco was asking, so this congestion controller, where in the pipeline is actually implemented, right? That's the question. So like I said, so sort of the first trick that we do here is separating the scheduler into two subtasks, right? One of these subtasks we executed at the very beginning of the pipeline. The other part of the scheduler process we executed right after the blue deadline that we have set here as a magical number, right? So the congestion controller runs on both sides, on both schedulers. So inside this, in the first stage of the scheduler, so here I have a sort of a congestion window inside the scheduler. That is the one that the scheduler has to obey. And then there is an algorithm that controls the congestion window. So essentially, this is a very simple approach because we don't have to change the regular scheduler. Whatever scheduler the base station implements, we don't change it. We just put a limit on the amount of bits that you can use based on this congestion window. So it's a maybe you are sleeping. Okay, so I'm not gonna spend. I'm gonna be very quick. I'm actually not gonna explain all the performance evaluation that we did, but essentially we implemented this approach in the physical layer of SRS run, which, as I said before, that I wanted to present is for the Downlink. So we first started evaluating the Downlink side of things. So here you see two plots. One presented the throughput of one base station. We have only one base station in this system. And the other one shows the delay, basically the computing capacity of the encoder. Essentially, the amount of time that the encoder needs to encode data, every single bit. So essentially, we play with the time to generalize the concept of computing infrastructure. We actually play with the time it takes for the decoder to encode every single bit, right? We start with the best that our off-the-shelf server gives us, and then we start delaying the process gradually just to test worse encoders, right? And we see the effect that has on both the baseline approach, which is essentially the regular pipeline of operations without Nuberu, and Nuberu for different parameters on Nuberu. I haven't explained what this lambda is. Just don't pay attention to it. I'm not going to explain. It's just a simple parameter that has to do with the congestion controller, basically. So it's a measure, a parameter that says that the aggressivity of the congestion controller. That's it. basically when lambda is infinity, the aggressivity of the congestion control is 0, no aggressivity. So essentially, the base station tries to transmit as much as possible without caring about use of computational demand. If lambda is very small, then I'm very friendly or very scared of using computational resources, and therefore the throughput go down. That's what you see here, basically for Nuberu. Of course, baseline, and this is what you saw in the first experiment that I presented here. At some point, it completely collapses because the encoder takes so long that the whole pipeline of tasks cannot finish in 3 milliseconds, and the user loses synchronization with the user. As simple as that, right? However, especially if we don't use our congestion controller, we can have 100% throughput, irrespective of the time it takes for the encoder to kick in, right? Of course, it has a price in terms of latency, because if we don't have computing resources, we keep delaying and delaying the data. That makes sense. So the second experiment, in the second experiment, we have both uplink and data. Here I presented for 4 cases, for 4 different computing capacities, which are characterized by this term K. Since K tells you the computing capacity of the system. If K is equal to 1, this is the nominal computing capacity of our server, the best we can achieve, but we keep delaying, slowing down our server, basically, by a factor of 2.5, by a factor of 4, and so on and so forth, right? So we slow down the computing capacity of our server for different plots. And here we saw the uplink throughput on the y-axis versus the downlink throughput in the x-axis, sort of a measure of the computing, of the capacity region of our base station, networking capacity region of our base station. Now, in ideal conditions where we have the ideal server, all the base station, Nuberu, with all the parameters of Nuberu, with HARQ, without HARQ, and the baseline performs the best, right? So there's always 100% of downlink throughput, 100% of uplink throughput, right? But the story changes when we slow down our server. And I'm not going to spend a lot of details in this scenario, but what you can see clearly is that for the baseline, particularly when we slow down the speed of the server sufficiently, the baseline collapses, which is the same point I've made before. And of course, between different configurations of Nuberu, there are different trade-offs between throughput and delay, which I'm not going to get into today. Interestingly, however, if you look at the purple line and the worst conditions where we slow down the server by a factor of 5.5, the purple line, which is the most aggressive configuration of Nuberu, we practically achieve 100% of capacity of the system, 100% of spectrum efficiency in the system, both in downlink and in uplink. In downlink we lose a little bit, but I mean, is quite impressive, I think. The last experiment, and with this I will conclude my presentation, is okay, we took one base station with Nuberu or without Nuberu. We place it in the same server with different instances of a baseline distributed unit. So instead, I keep placing competing instances of a distributed unit at a certain load, each of them, right? So as I increase the number of competing videos, I also increase the computing capacity of the system. This really doesn't say much or new things with respect to the previous results, but essentially, instead of slowing down my server, I increase the competition. But the effect is more or less the same, basically. When I increase the competing videos, I also reduce the computing capacity available for the distributed unit that I'm testing here, and the result that you can see is basically the same. At some point, again, the baseline collapses, whereas in the case of Nuberu, we hold the fort quite nicely. And this is it. I don't even have a concluding slide. I think I made the point very clearly. So this concludes my presentation, and if you have any questions, feel free to ask.
Thank you, Andres. Are there more questions in the audience or online?
Yes, Marco has one question.
Okay, please go ahead.
They're not going to hear him even so it doesn't matter. Yes. Sorry, Marco will make a question and I will repeat.
Okay, thank you.
So let's say the current approach of using an accelerator you any strong guarantee.
No.
It's just that you also dimension.
Exactly. So okay, what Marco asked is, okay, with the approach of actually using a dedicated hardware accelerator, or not dedicated, just by using a hardware accelerator, even if you use one hardware accelerator, you still have no guarantees that you will meet the deadline, and that's entirely true.
So you can potentially apply this to
Exactly. Yeah, we can. Exactly, we can apply this to systems with hardware accelerators. Definitely. In fact, this is thought for scenarios, for real scenarios where we have a hardware accelerators. Only they're shared, because if you have one hardware accelerator and one base station, you are really over-dimensioning a lot of the system. So even though there are no guarantees, like mathematical guarantees, that you can meet the deadline, it's hard. That's right. Right, or if you upgrade the implementation of your base station and I don't know, whatever. Yeah, even if you use hardware accelerators, there are no guarantees on reliability. It's just you try to overdimension as much as possible in the hope that this happens. Now, this is a very, very good point, Marco, because this is actually our argument that even if you have an appropriate computing system, computing infrastructure, even though you have a very good CPU scheduler or a compute scheduler, even with hardware accelerator, which is what, for example, the second paper did. Essentially, it's a task scheduler. If you have the optimal scheduler, you may be improving tail latency, so the tail of the distribution latency, but you still have a tail. You still have a tail. So you haven't solved the problem. You have improved, certainly, and no question about it, but you haven't solved the problem. So what we claim here is that if we look at the implementation of the software itself, so the application itself, if we engineer this application in a different way as we did here, we actually solve the problem.
Okay.
Yeah.
So let me ask a question from my side. So in the past, you've done some nice control theoretic work. I can recall you in Infocom 2012 paper, right? So here you're talking about a collection of kind of simple hacks.
Yeah.
So again, maybe it's more general question about this work, but in general about things which have a practical value. How do you see this role of kind of theoretically guided design as opposed to something kind of more ad hoc?
So I think here for this feedback loop, you can actually implement some probably better designed control theoretic approach, like a simple PI controller, right? Because they are lightweight. That's what matters. That algorithm that you do is lightweight. A PI control is also lightweight, so you don't really need to do a lot of computations to actually get the solution to your problem, right? So certainly that. So here we went for a very simple TCP-like approach, just for simplicity, but certainly like a PI control could work. Now, what I will claim is that placing a neural network here would not work, right? Because either you place the neural network in a GPU, which, okay, the whole point here is you don't have resources, or you're stealing a lot of CPU cycles from the CPU that you cannot afford.
Okay. Also, you talk about real-time deadlines. And do you think that something from real-time scheduling theory is applicable here as well?
Sure, yeah, definitely. I mean, this is essentially, this is very related to the question that Marco just did, is, for instance, this paper from SICOM this year. What they did essentially a real-time scheduler. They tried to schedule these tasks into the computing infrastructure to make sure that the latency constraints of the base station are met, right? They try to do it. And this is certainly very important. So we should have a real-time scheduler in this case. We just decide not to have it, just to have a bad scenario, let's say, but you have to have it. Now, the claim that I just made for Marco's question, which is very similar, is even if you have a real-time scheduler, the optimal scheduler for this problem, you cannot solve the problem because you will always have a tail in the distribution of your latency, and therefore you cannot guarantee 100% reliability of the system. However, if you actually re-engineer the application itself, we can actually achieve 100% reliability of the service.
Okay. All right. I don't see any questions online. Are there more questions in the audience?
No, only sad faces.
Okay, well, we already had a seminar for 1 hour, so I think we fully utilized our slot. Actually, let me see. There's a comment maybe from HARQ, or maybe a question. No, HARQ does have questions, so let me read them. Is there a meaning for Nuberu? And 2, when would computing interference happen due to lack of resource? So I think, first of all, does the name of the of your paper have any meaning? I guess in the second.
So you're asking for Nuberu, the word Nuberu.
Yeah, I think so.
Yeah, this is probably something that Pelayo or Narceo can answer better than I do, because that has to do with the mythological figure in Asturias, in the north of Spain, where Narceo and Pelayo are from, actually. So that has to do with sort of the ruler of the clouds, is related to clouds, and that's.
I see. And the second one, yeah, and the second one, when would computing interference happen due to lack of resource?
When, well, as soon as you have multiple contenders for computing resources, you will have computing interference, because you have a user using computing resources and you have another one stealing them, creating interference in terms of computing resources. So as soon as you are sharing, you will always have this interference from other instances of a station.
Okay, so I guess this is a good point to close the seminar. So let's thank again Andreas for the presentation and for coming here. Thank you.
Yeah, thanks. Thank you for coming.
Thank you, Andres.
Thank you.
Thank you very much.
Bye.